from glasses to multicellular systems. Our talk today will focus on emergent mechanical properties of biological tissues. So, Lisa.
Thanks, Sheila. And hi, everyone. How are you? So this is the second lecture in a row. And the first one was really good. So that's annoying because now I have to live up to it. Also it means that we might have to have like a jumping jack break in the middle because like 3 hours of lecture is a lot of hours of lecture. And also the people who were here early told me that they wanted me to write on my tablet instead of on the board. So we're going to try that today and see if you like it. And if you don't like it, then we won't do it anymore. You can vote, okay? But we're going to try it that way because the people who were here in the room real early told me so. So, haha. Okay. All right. The idea here that I would like to talk about is I'm interested in emergent behavior, and I'll say what that is in a minute. But before I go any further, I just have to say a lot of my understanding of what I'm going to talk about was really shaped by all of the lovely people that I've worked with, collaborators, and also the fantastic students and postdocs in my own lab. So I just wanted to give a quick shout out. And so Mielo's in the audience. So she's one of the people you could talk to if you have more questions about stuff, because she'll actually know the answers, unlike me. And here is, and I'm really going to try to emphasize where sort of the third lecture, if there's time, I may get to some like newer research results, and then I'll highlight the people who are doing the work actively, but we'll see if we get there. It seems like y'all ask a lot of questions, which is awesome. So we may not, and that would be great too. Okay, and so the question that I want to start with is, how do you turn a blob of material into something that's the shape of a fish? So animals start out as spherical objects, roughly speaking, and you need to turn that spherical object through the process of development. So this is a zebrafish embryo. This is the yolk, and these are the cells that are going to become the zebrafish. And you see that they divide and divide and divide. And then there's a certain part called the shield stage where they start moving and flowing in a beautiful pattern, sort of along the edges of the yolk. And over time, you can see that there's somites and vertebra forming. And then there's the head and the eye and the tail of this organism. Okay, and so that seems like a pretty complicated problem. How could we ever try to answer that question? It seems a little daunting, actually. But I would say that there is a problem for which we do know the answer. So actually, glass blowers know exactly how to do this. They start with a blob, right? This is a blob of glass. And then they change it into a beautiful fish. This is actually one, I got so lucky. I actually purchased this for my kid in Venice before I gave this talk. I was like, oh, it's a perfect example. It's a fish. Okay. And so the idea is that you can make a complex, stable, reproducible morphology if you're an excellent glass blower. And the way that you do it basically is you apply localized forces. So you use like a special table and what's called a Manjot rod to apply, specific localized forces to various places in the blob, right? And you also, and this is really key, this is why people use glass, you use heat. And for glass, you use heat because it alters significantly the local properties. So Ulrich already told us, Professor Schwartz told us about how we had a constitutive law that told us about how a continuum material behaves. And there's one sort of rule or constitutive law for solids, right, where you have a modulus that says, oh, the stress is proportional to the strain. That's one type of emergent behavior of a material. Or I could have a viscous-like behavior where the stresses are proportional to the strain rate, how fast I move the system. And there's a transition between potentially, and in fact there is in glasses, between a material that has an elastic constitutive law to one that has a viscous constitutive law. And actually there's a lot of complexity, viscoelasticity in between those two extremes also that maybe I'll talk about a little later if there's time. But for glasses, the cool thing about them is they go through what's called a glass transition. So they can go from solid to fluid to solid. And the way that the glass blower uses this, of course, is in regions that they want to take the blob and they want a large strain in that material, they heat that region up. Because, of course, it takes a ton of elastic energy to strain something that's a solid. but it takes very little energy to pull and strain and deform something which is a fluid. So they heat it up at exactly the right place where they want to stretch it out. And then at the end, of course, you don't want the thing to be a fluid at the end. You want this nice functional form of the fish. And so it needs to turn back into a solid again so it can support shear stresses and be functional. Okay, that's kind of cool. Okay, and so I'm going to focus for actually all of my lectures, I think, on this question. And so you might say, okay, that was a nice analogy, or maybe it was a bad analogy. I don't know, but it was an analogy. And you can ask, is something like that really happening in a embryo, in the zebrafish embryo? So here's another lovely little movie of, where this is sort of state-of-the-art labeling of the cells. This is a more modern movie of that same zebrafish development. And you can see there's some really beautiful and complex flows that are occurring here. Okay, and you can say, well, is it mostly the force changing, the applied forces that are changing in order to generate these shape changes? Or is it the material properties, or both? How do you figure it out? Right, and so I would say that there is a couple of papers that I want to highlight, and I'll come back to these a little later. Again, at least for zebrafish, there are two stages in which you can really, really see that there's a fluid to solid transition, that the material properties are changing dramatically. Yeah, there's a question. Oh, the movie, yeah. Yeah, so that initial movie I showed you, there's a yolk inside. So the way that, because you need a huge energy source for all the ATP, you need to do all this stuff. And so the way zebrafish work is there's this big yolk, and the initial development happens basically on the exterior of that system. That's what you're seeing. It's a great question. It wraps around, and there's like this cool pole, and there's all sorts of weird stuff that happens at the pole, because of course it's topological. Great. Okay. Okay. And so this set of experiments is at a later stage of development in the zebrafish tail bud. So you know how I showed you there was that tail at the end of the embryo? It turns out actually there is a spatial gradient in the fluidity of the tail bud. It behaves like a fluid at the very end, and it behaves like a solid up here. And that actually, this paper argues, is important for the elongation of the tail. This one is more recent. It's so cool. Edward is going to be here and lecture to you. And this is like an amazing paper. It's amazing. And what they do is they show that shield stage of the zebrafish, which is this picture with the ball of cells on top. It basically undergoes a rigidity transition. And they've gone out and they've traced the contact network. You know how Momita Das gave a lovely lecture earlier? The and contact works. We are going to revisit that again. And this says, and I think she even showed a picture from this paper, that the contact network changes from being a percolating rigid network to non-percolating right at the point where this thing has to start straining itself. In other words, it's programmed to change its material in exactly the way that allows you to have very large strains right at this precise moment. How cool is that? Okay, cool. Okay, but it's not just cells that have transitions. And again, Professor Das talked a little bit about this, although we're going to continue to talk about it. In extracellular matrix, which often exist in disordered networks, original work by Margaret, and then others have shown that there is a really interesting what's called strain stiffening behavior. And so there's two important parameters, and we're going to talk about these a lot more. This axis is basically the connectivity, which is how many branches the extracellular matrix network has, roughly speaking. And this axis is how much you've strained the box. And so if you're above isostaticity, and we'll talk a bit more in a moment about what that is again, then you're always rigid. But if you are below this isostatic point, you'd think you'd be floppy, but it turns out if you strain the box, you can become rigid again. You can take the box and strain it, and all of a sudden the material stiffens by orders of magnitude. And so I would say these are two types, either going across this way by increasing the connectivity, or going this way by increasing the strain, are types of rigidity transitions that also happen in non-cellularized tissues. Okay. I just want to say a few more words in case you're interested in other systems other than tissues, because those were two tissue scale things. Of course, rigidification has been shown to happen in liquid-liquid phase separated droplets, and it's been implicated in disease states for those systems. We heard a little bit, and I think we'll probably hear more, that a cytoskeleton inside a cell can tune its rigidity, and there's a limit in which it can behave like an active gel, and so we'll hear more about that from Professor Schwartz. Okay. And the other thing that I'm not going to talk about too much, but I'm very excited about, is thinking about how you can control this type of behavior at the scale of organs and organisms when all of your control inputs are down there. Like, you know, DNA programs the stuff, the output is at this scale. What is a robust control strategy for that? Because, of course, if you understood what the material properties were of your embryo, then you could say, oh, I know exactly where to apply the localized forces in order to get the shape I want. So I guess I would say that what I'm talking about in my lectures is step 1 of this program, but then there needs to be a step 2, which is how do I robustly use that information to program things? Does that sort of the idea make sense? Okay, and so, you know, I think the other thing is that, of course, like I think of myself both as a biophysicist and as a soft matter physicist, and I think like, as if you're a material scientist, you'd love to be able to make materials like this, right? You know, I used to show a part from the movie Terminator 2. Are any of you, I'm old, so like Terminator 2 was a big deal for me. Yeah. Yeah, I know, with the robots. But I like actually Terminator 2 better because he's really a material. It's not nanobots, right? It's a material. Okay, but I stopped showing it because I used to say I wanted to make Terminator 2, but that seems bad. Like, I don't actually want to make Terminator 2. He tried to destroy the world. But I think it would be really cool to think about what you could do if you understood these design principles in biology, where you were able to dynamically change the material properties and apply localized forces in such a way to generate morphology changes on command, right? I think that would be a great goal. And so, you know, a challenge of that. So first of all, the first challenge is, okay, as we will hopefully learn over the next 3 lectures, emergent rigidity is hard. Studying emergent rigidity in disordered systems is non-trivial. Okay, challenge 2 is that, well, actually in biological systems and maybe in materials, you have many, many tunable parameters. And the tuning parameters are at a smaller scale than the emergent behavior, so how to control. And Andrea Liu is giving a series of talks next week, and she and I have been collaborating, and there's a lot of other people that are thinking about certain pieces that she'll tell you about. So I'm not focusing on that, but I hope she will connect up from where I leave off. So look forward to that. Okay, so why is emergent rigidity difficult? And so, you know, I sort of also occasionally think of myself as a condensed matter physicist, and then you have to have an obligatory quote by Phil Anderson, I feel like, in every talk if you're a condensed matter physicist. So what he said was, we are so accustomed to the rigidity of solid bodies, the idea, for instance, that if I have a ruler, right, and I push on one end and the other end moves the same distance, this is a solid. Why does it do that? You know? Okay, you might be like, of course it does that, Lisa. But why? Like, explain why in terms of math. It's not trivial, right? But we don't accept its almost miraculous nature, that it's an emergent property not contained in the simple laws of physics, although it's a consequence. Okay. And then he said, and this one's a little bit more annoying, the deepest and most interesting unresolved problem in the solid state theory is probably the theory of the nature of the glass and the glass transition. And since I work on glasses, I use that quote sometimes, but it's a little bit obnoxious. So, okay, fine. Okay, so we're going to work on this challenge basically for the next 3 lectures. That's our job. Okay, so Professor Doss gave a fantastic introduction to this topic the first week. And so I've reviewed her lectures, and what I'd like to do is build on them here in a slightly different way. So Professor Doss focused on semi-flexible networks, and especially on effective medium theory as a way to solve those types of problems or make predictions, which is really cool, and composite networks. And so here we're going to be extending those ideas in some different ways. Okay, and so, you know, it turns out that in biology, I think, and especially at the scale of tissues, there are multiple mechanisms that can drive rigidity and fluidity. And so like a while ago, a graduate student and I wrote this opinion that was sort of a little bit more geared towards biologists, where we said, okay, there's sort of okay, there's actually many more than 3 axes, but here's 3 axes on which you can think about rigidity transitions. So one is that you can change the density. Like if I pack the objects in my system closer together, I expect them to become rigid. That's along this axis. And so the gray area is the solid. And this is a phase diagram of a transition. Okay, and then the other thing I know is that if Professor Schwartz already talked about high temperature behavior, right? So if I add more and more fluctuations to my system, I expect that if I take the same system and I add a lot more energy and fluctuations to them, I might be able to fluidize the system in that way. This third axis, I would say, is a little bit underappreciated. We call it a geometric incompatibility axis, and I'll walk you through what that is. It shows up in both fiber network models and in vertex models for biological tissues. And so this one, I think, is used a lot by biology. And so we're going to talk about it a lot because I think it's one of the things that is harder to find in the literature. Okay. The other thing oh, yes. No problem. I always get confused about like 1 over variables. So did you have a question, Leo? You're a ringer. Yes. Yeah. Okay. So, and I'll talk, that's a real, so the point being is that actually what I said was false. It's true that if you increase the fluctuations, you actually fluidize the system. Entropic contributions can sometimes rigidify systems. And I'll mention that detail a little later, but you're exactly right.
So you increase temperature and go on place again because another
yeah. Yes. So I guess I would say is that this particular, and it's not an excuse, but this particular diagram was talking about cellular systems for biologists. And kind of in general, though it's not always true, for these cells, because there's actually easily all of these, not all of them, but most of them, if you're talking about cells, facilitate cell rearrangements. Fluctuations often lead to cellular rearrangements that dissipate energy. Unlike elastic systems, when you add entropic contributions, they sort of basically straighten them out a little bit. Well, put them under more tension effectively. Okay, but that's a really good point. There's lots of, yes? Yeah, so this is actually this line is dashed because there's some evidence for what the shape of this is like from some really nice work by Oche Campas and collaborators in active foams, and also Corey O'Hearn and collaborators in deformable particles. But this is conjectured, and the exact origin of whether there's actually a kink in its behavior is still under active investigation. It's a good question. The shapes of these two are pretty solid. That's why they're solid. Yeah. Oh, that's a really good question. Can you save that question? Because I will actually address it later when I get on the board. Okay? It's a really good question. And if I don't address it, point it out to me, okay? Okay, great. So the thing I'm going to tell you right now, because of all the hard questions I just got from the peanut gallery over there, for these lectures, we're mostly going to focus on the zero fluctuation limit. And the reason why is because I want this to be really pedagogical. And of course, finite fluctuations are important. It's often the case that if you understand the zero fluctuation limit, you can understand features by extrapolating into the fluctuations. And one of the open problems I gave is about thinking about that too. But just so you know, I'm going to focus mainly on here for the lectures because it's really, I think, clear, and you can say things most straightforwardly. Okay, so here's an outline, just so you all know where we're going. Today, I'm going to focus on this 1 over density axis. So basically along here. And the math of it, okay? And then in the second set of lecture set 2, on day 2, I'm going to focus on this one, okay? And so you know, this is sort of an outline, because I'm also going to post these online so you have it for future posterity. Tomorrow's lecture is that other axis, that geometric incompatibility axis, as well as going through, I think, some more complicated example model systems like vertex models that generate that type of transition. And then we'll talk about a little bit about finite temperature, maybe, or dense active matter, maybe. And then I want to talk a little bit on Wednesday, depending on what you find interesting and what there's time for, thinking how you can design or evolve specific emergent mechanics in along either of those two axes. Okay, that's where we're going to try to go. Okay, so now I'm going to switch to the tablet and cross your fingers that everything goes okay with this transition. We'll see if it works. Okay. And let me bring up this. All right. And I got to turn this on so that it actually knows that something's connected. Okay, perfect. Okay, good. So we'll try using the tablet today, and if enough of you hate it, we'll switch back to the boards tomorrow. Sound good? Okay. So the first big picture question is, how do you determine if a material is rigid or floppy? And I would say for many people, or for some people at least, especially if you're trained as a physicist, so, you know, is a material floppy or rigid? And the answer for, you know, physicist, here's the physics answer that you get if you look it up in a textbook. The first point is that it's usually stated in physics textbooks for crystalline materials, because we understand solid state physics, and it's Ashcroft and Mermin specifically that everyone uses, right? And what does Ashcroft and Mermin say? I'm just going to reproduce what they say. Okay, what they say is it's a crystalline material, so it's a set of lattice points. You start out with the lattice points, and Ashcroft and Mermin call that R. So I'm going to use Ashcroft and Mermin notation for this. Okay, and then of course, so here is the Bravais lattice, the set of points R, which is a true lattice, which means that I can take a Fourier transform and get a well-defined wave number. And then I can say, okay, in a real crystal, there's fluctuations around that Bravais lattice. Yeah. It's too bright. Okay, maybe it's possible to reduce the, I have no idea. No, maybe I could do it on my screen. I don't know if I can. Okay. Okay. Yeah, okay, I'm sorry. No, but I'll take into account that it's too bright for some people as a reason to use Blackboard in the future. Okay, so here is the displacements. Oh, yeah. I would prefer not to do that if it's okay. It's a good suggestion, but I think it might be problematic. Okay, I'm going to keep going for now. Okay, so here are some basically displacements, you know, fluctuations, and we'll call those U. Okay, there's these little U's away from the Bravais lattice. Okay, and then if I have some coordinate system, right, then actually the total location of each actual like atom in my lattice is given by a little r vector, which is a function of displacements away from the Bravais lattice. Okay, and so then I say, okay, the actual location is this R of capital R is capital R plus these U's. Okay, and then you already saw, I think, from Momita's, Professor Das's lecture, that I can basically think of the energy, the total energy, and I'll try to use U for the total energy of the system. It's basically a constant, okay, plus something that looks like this. So you can write it to harmonic order as the sum over Bravais lattices and indices of U of R, and then this is the dynamical matrix, which I think you were already introduced to by Professor Das. Okay, and then this little U of R prime. Okay, and this object is called the dynamical matrix. Great. And why don't I have a linear term? I just have a quadratic term. a stable, right? It's a stable solid. So if there was a first order term, then there would be forces that are moving it away from that capital R, right? So I don't have a first order term for a solid. I just have a second order term. Okay, good. We should say too, of course, this is only an approximation. There actually are higher order terms here, but I'm just not writing them. Okay. So the next thing is, because this happens to be a crystal, is like assumed in all of Ashcroft and Merman, we have basically that the symmetry, because of the symmetry of the lattice, we can take a Fourier transform, or if it's easier for you, we just assume a solution of the form. The u's are proportional to e to the I k n a minus omega t. And the reason you assume this form, right, this is the lattice spacing for the Bravais lattice. And that k is now a wave number. And again, we can only get away with this because of the symmetry of the lattice. Okay, but then because of the symmetry of the lattice, this ginormous, right, this matrix has in it the dimensions of the Bravais lattice right now in real space, right? It's as big as the lattice, right? Because it has R and R prime in it, right? It's, the size of a crystal, Avogadro's number big. But because of the Bravais lattice, we say, oh, once we take this Fourier transform, then we get something really simple. We have all of the spatial information basically as a wave number now in K, right? And this is a matrix, then a very small matrix that we can write an eigenvector, eigenvalue equation for. This basically says that once I take the Fourier transform, the dynamical matrix D is diagonalizable, okay? And it has real entries. So this is eigenvalues, okay? And this is eigenvectors, or these for vibrational modes are often called normal modes. And I'll use normal modes a lot in what follows, okay? And because all of these lambdas, okay, so this object is now a 3 in 3D, and it's a 3 by 3 matrix, which has like the X, Y, and the Z sort of directions. But I got rid of all those R's by taking a Fourier transform. So I've replaced all the R's with a K, and then I can just index it by K. Okay, cool. And probably some of you have taken solid state physics, have seen this a million times. I'm just saying it in this way because we're going to use it again in a really weird and different way later. Okay, but this is to remind you of maybe things you know. And I actually was lying a little bit. This is a 3B by 3B matrix if I have basis, right? So this is the number of basis points for those of you who care in my Bravais lattice, in the crystal, okay? And I can also think, because it turns out that this D is positive definite. Why does it have to be positive definite? Looking at this equation. Otherwise, it's unstable again, right? So it doesn't have a first order, this expansion doesn't have a first order term because that would mean forces. And if I had any directions of negative curvature, right? These are curvatures of the potential energy landscape, right? And if I had any negative curvature directions, I could go down them, right? So this is positive definite. That's what allows me to do this normal mode analysis, right? There's a famous theorem in mathematics that says I can do this now, right? And so I'll write that down in words. Basically, we know that D is diagonalizable with positive eigenvalues, which means I can think of these eigenvalues, lambda, as defining a characteristic frequency. If I perturb the system along a normal mode, it will ring with that frequency. This M is just a mass. Okay, it's just an oscillating oscillator. Great. Okay, so this is the physics definition. Okay, and the fact that, maybe I'll sort of write it out in words, the fact that lambda is greater than 0 means that any small perturbation U, which can be written as the sum of these normal modes, because the other part of the math theorem is that those modes span the space, right? And they're orthonormal basis. So yay, okay. So I can write any perturbation as a sum over these little normal modes. Okay. Any perturbation generates a restoring force that drives the system back towards the lattice points. So this is the Ashcroft and Merman answer. So if you say, why is a solid rigid? It means that there are no perturbations, and I promise there's a reason I'm being so pedantic, sorry, but there are no perturbations. It's not possible to have a perturbation U to the lattice that costs 0 energy. Cool? That's what it means to have a crystal lattice. That's a nice feature of it. Okay, so that was lovely. What about disordered materials? So all of that follows from the fact I could do all that nice stuff to that Bravais lattice. So what about disordered materials? So first of all, I think you talked about this a little bit with Professor Das. What are some examples of disordered materials? What are we talking about? Glasses, yes, glasses, one of my favorites, also hated. What else? Granular materials, sand piles, you know, mudslides maybe even, could be directly relevant to humans. We heard something from Ulrich. Polymer networks, yes. I thought for sure that side of the room would have polymer networks and also composite networks made up of multiple different types of polymers all together. What else? Cells and tissues, yes, they are disordered. They're not on a Bravais lattice, yay, okay. Oh, and my other favorite, piles of ants or groups of bees. Have you seen this cool work? Super cool. Okay, so there's many like collections, collectives of organisms also have this structure. Okay, I'm sure there's more, but that's a good starting point for all of these things. Okay, and I would say in Professor Das's lectures, you learned a lot about sort of polymers and fiber networks. And so today we're going to focus maybe on those other classes mostly, although we'll come back. Okay, so the other thing that I'll say before I go forward is that, okay, if we're interested, let's say first in glasses or granular materials, and that's going to be a case where it's pretty easy in both of those systems to think about density as a control parameter, right? Like as I add pressure to one of those systems, the material properties change dramatically. So this is that 1 over density axis. The thing I'm going to say right now is that glasses are really interesting and challenging at finite temperature. And so the reason why actually is because it turns out, oh, I'm not going to be able to flash back up, so I'll just draw a picture. You know, I had that diagram on the slides that sort of had fluctuations and up here, and then there was a 1 over density axis here. And then there was this other weirdo one called something, I don't know. Okay, but this point here, I drew as a point. And I said, oh, there's a curve that says how as I turn on fluctuations or temperature, the rigidity changes. And what I'll say is, I'll come back to it in a little bit, maybe in the third lecture. This is actually a lie, and it's a very interesting lie. It turns out actually that if you come down from finite temperature to 0 temperature, that's the glass transition, and you turn into a solid at a different point if you approach from finite temperature than if you go along the 0 temperature line. Okay, so this point is not a point at all. It's a very complicated not point. Okay, and so I'm going to ignore this for now, although it really leads to interesting behavior. And there may be some interest when you start to think about how evolution or programming of cellular materials where 1 over density is an axis, how they might use the fact that this point isn't a point to program things. Okay, and we'll come back to that at the end. But for today, you just need to know that it's not a point and that now I'm going to ignore it and just go along the 0 temperature axis. Okay? Yes.
Is it given the finite speed of particle, it was equilibrium?
That's a really good question. I hope to get to this a little bit in the third lecture. The short answer is no, because the viscosity diverges as you approach this point. It actually turns out that there's actually a whole spectrum of points here that you get as you fall out of equilibrium. And there's a beautiful transition called the Gardner transition that happens explicitly in infinite dimensions, but actually seems to be relevant for finite dimensions, that explains actually in a beautiful way and with results that are quantitatively correct how this not point situation happens. And I will try to go over that a little bit. And if folks are interested, I can either talk in the things after. There's a nice review article I can point people to if you end up being interested in that. But it's not going to be my focus for today. Okay, so let's do t equals 0. That was a long-winded way of saying let's ignore all of that and do t equals 0. Okay, limit of repulsive spheres, and they don't have to be repulsive, but repulsive is easiest. If they get too far attractive, then you get gelation and another interesting set of things. But it is simpler, okay? And we're going to talk about it. And we're going to talk about rigidity in it. Okay, so the setup of the problem, so you have a box and you put some particles in it. And they're spherical and they're repulsive. Okay, so here is a picture of a box. You can make it have periodic boundary conditions or not periodic boundary conditions, are a little easier from a theoretical perspective. Okay, and so each one of my particles is defined by a center and its radius. So I'll put a little r for the radius of the particle. Okay, and I have n particles in d dimensions. So I'll start talking about dimensionality now. Okay. And of radius r. And sometimes we'll make r 2 different values of r, but I'm not going to focus on that now, capital R. Okay, so then the description of the system is in terms of an r sub I, which is the location of center of particle I. Okay, and I'll draw a little picture, for example, to the center. And actually, let's make these 2 touch for my drawing here. Then I can talk about them. Okay, and this will be, let's say, 1 particle R1, and that's the distance there. And then I could have a second particle nearby, call that particle number 2, and this will be R2. Okay, and then I can think about the chord that connects them. And this, the notation for this in the literature is Rij or R12 in this drawing. Okay. Okay. And so when I'm thinking about this, as you've already learned from Professor Das, I want to think about the number of degrees of freedom per particle. So if this is a 2-dimensional disk packing, how many degrees of freedom do I have per particle? 2, right? Can you show me with your hands? Everybody do the dance. What are the 2 degrees of freedom? Show me with your hands. Up and down, right? Left and right, right? Okay, those are the 2 degrees of freedom. Good. Do you know that all of you have like research dances? Yeah. And so, this is like the freedom, degrees of freedom. I'm going to do this dance throughout the lecture. This is the degrees of freedom dance for a 2-dimensional system. Okay, so there are d degrees of freedom. I know it's a pathetic dance, it's true. There are d degrees of freedom per particle. per particle. So in 2D, we have this is 2D, okay? And in general, we consider a two-body interaction between the particles. Okay, so if we define Rij is equal to Ri minus Rj, right? Looking at this picture, right? You know how you like do it geometrically, you like put the tail in the head of this one and add it to the top of the other one, and then I get this one. That shows you which direction it goes, right? It goes in Ri minus Rj, and that's the convention we'll use. Oh, did I do it wrong? Goes from 1 to 2. Does it? So if I draw this one backwards, right, then it goes, oh, I did do it backwards. Yep, it goes this way. I drew it backwards in my picture. Thank you. All right. Great. Okay. Then the force, for example, between particles I and J, if they're repulsive spheres, people often write in this way. There's a constant, and then it looks something like this: Rij hat if R is less than the sum of the two radii, and there's some power here. If it's a harmonic potential, then alpha equals 1. Sometimes people look at Hertzian potential. Alpha can be 3/2. It can be a different power if you want, and it's 0 otherwise. So what this means is the particles aren't touching, they experience no force, and then as they compress, there's like a half spring that penalizes them as they go. So, because it's going to be interesting later, you could write this instead, if you wanted, as like a K times an L minus an L naught. So this looks like a spring with rest length L naught, where L naught is 2R. Okay, but it's only a half spring. If you go beyond where they touch, then it doesn't pull back. Okay. So then you already learned that if I want to think about whether this system is rigid, then each contact I have, each contact between a pair of particles introduces a constraint on the motion of those two particles. And, using English words, it costs energy to move them closer together, right? That's what this says. Okay. So let Z be the number of contacts per particle. We'll use little z, number of contacts per particle. Okay. Then there are Z over 2 constraints per particle. Why do I divide by 2? Yeah? Yeah, it's shared between two particles, right? So I'll just write that each constraint is shared. Okay. Okay. And so we have Z over 2 constraints, and we have D degrees of freedom. Okay. And I'll sometimes write that as DOF for these notes. Okay. And then what's our intuition? If I want the system to be precisely rigid, as you already learned from Professor Das, I said these two things equal to each other, right? When these two things are equal, that's when I become rigid. So I expect there's a critical number of constraints, I'll call it Z sub C, where these two things are equal. And this says that ZC equals 2D. So you already seen our first place where dimensionality enters the problem. It basically tells you that how the number of constraints I need scales with the dimension for a system like this. Okay, great. This is called isostaticity. That Z sub C is the isostatic point, isostaticity. It is also called constraint counting. And I know you've seen this already, but I promise there's a reason that I went through it a little pedagogically here. It also, by the way, totally works. So like for jammed packings, this is exactly right, which is kind of a miracle because it's a mean field argument, actually, right? It's a mean field expression, but it works exactly well for like, a jar of Teflon coated marbles or an experiment on peas, you get exactly this number in any dimension. Yeah. Oh, that is a very good question. No, and in a very interesting way, because you have rotational degrees of freedom. And so you think it should just change the isostatic number, just jump. But actually, it turns out because friction introduces forces, as you change the friction on your ellipsoidal particles, you can actually get a continuous transition between spherical and ellipsoidal dynamics. And it also depends on sort of, well, maybe that's an extended discussion, but I'd be happy to discuss more. Yeah. Yes. Well, that's a really good point. What I meant is for jammed particles, there is a small fraction of things that are under constrained, and those are called radial loops. Actually, you can think about them as not. And all of the other particles have exactly this number at the transition point. Spheres, this is like totally mean fieldy argument is exactly right, which is a mystery. Well, I think it has to do with the Gardner transition that I mentioned earlier, but we can discuss that more later. Yeah. Go ahead. Oh, no, alpha doesn't matter at all for this fact. It changes scaling behavior. So if you look at how pressure scales with density, there's beautiful scaling relations. There's a whole lot here that I'm not going through, and alpha changes many things. It does not change this fact. Okay, so that's cool. Now, the reason why I went through all of that is I would like to explain why it works in such a way that we understand when it breaks down. Okay, because this was a crazy, honestly, it was a crazy argument. Why do jammed spheres have exactly this number? How does that happen? That seems crazy, actually. Okay, so now let's understand why this works. So why does it work? Why? Okay. Now we're going to talk about it in terms of dynamical matrices. Again, we're going to get back there because we're going to do it the math, like true math way. Okay, so if we have a network where the interaction energy is a function of a set of constraints. So we have a network where the interaction energy can be written as a function of a set of constraints. And we'll call those constraints for the rest of these lectures F alpha. So what do I mean by that notation? Above, I gave you an example. So the Fij was K times L minus L naught. And this alpha is it's an index for the constraints. So here, there's a force associated with this constraint, and it might be related with the distance between those two particles, right? And I might even have a different spring constant for each of them if I want. Okay. Then I have for these systems, because these are potential systems and we're not paying attention to fluctuations yet, I can write the total energy as the sum over these constraints. And, for this particular example, it's quadratic. Okay, great. So the point is this object, just again, is F alpha, is the constraint on bond alpha in a disordered network. Great. Okay. And just to sort of say, this is good. This could be a spring network of the sort that Professor Das talked about a couple weeks ago for ECM. It could be a contact network for jammed packings, or it could be a vertex model. You can write all three of these things in exactly this form. So it could be a vertex model for confluent cells. Any of these work. They can be written in this form. Okay, then the key idea for today is the following. This is, I think, the most important idea, so I'm going to do it on a new page. So if I have a network, so now I'm drawing a network, I'm trying to draw at random, I'm bad at drawing random networks on the fly. It's always a bad idea. Okay, so these black points are the vertices. And in this first picture, the vertices are really the degrees of freedom. And there's some constraints that link these degrees of freedom, maybe. Okay, in this disordered network. And I've chosen some connectivity for this network. Yes. Oh, sorry, I went too fast. So all I did was give some examples that could be written in this functional form. And I'll go through those examples later, but I'm just saying all of these things work as an example. In other words, hopefully what you learn is applicable to a whole bunch of different systems in the world. Yes? Yeah, sorry. Yes, unfortunate notation. It's a different alpha, but this is what's used in the literature. So sorry, two different alphas. My bad. It can. I will sometimes assume it does not. It can. It doesn't have to. You can assume that the spring constants for all the springs are the same if you want. And we'll talk about that question of how important that is later. But it's a good point. Yeah. Yes. It does. It's a great question. The short answer is it does not make a difference if you're approaching the transition from the solid side. There's a lot of interesting behavior if you're thinking about the side that's floppy. And a lot of people have studied the behavior sort of on the floppy side in terms of like shear thickening of suspensions and stuff. So yes, but if you're approaching from the rigid side, it's okay. You're over compressing it a little bit and then asking in the limit that you go back down. Yeah, in that limit, everything is fine. And actually, lucky for us, the biology piece that I'll talk about, this beautiful work by Petradou, actually has that same assumption, so it's okay. But it's a good question. Okay, great. So now back to our disordered network. Okay, so, and actually, I'm going to be a little bit extra pedantic and say, okay, these are the degrees of freedom in this system. Oh, actually, you know what I'm going to do? I'm going to undo those. I'm going to use the fact that I'm working on a tablet today. Sorry that some of your eyes hurt because of it. But it helps me do this because then I can have the exact same image twice. Okay, and on this side, I'm thinking about the degrees of freedom as these vertices. And on this side, I'm thinking about the degrees of freedom as these bonds. And I'm going to be thinking about mappings from one description to the other description. That's going to be the key point. So we're going to say, hey, there's a map from thinking about configuration space. So we're going to do a mapping from configuration space, which I'm going to say, okay, is these x sub i's, these positions of these variables, and this I indices the vertices. Okay, those are vertices in the network. Okay, and over on this side, we're going to have a mapping to constraint space, parameterized by bond vectors. Okay, and those bond vectors, I'm going to call them L sub alphas. Okay, and then as before, thankfully, I'm not changing notation on you this time. This is still indexing constraints, this alpha. Okay, great. Okay, and the question we're going to ask, so we're thinking about going back and forth, and we're going to think about a map that takes us this way, and then a map that takes us back, and we'll call that the transpose of the map. Okay. Okay. The first question about this map is how big it is. So how many xi mu are there? And I'm using this little mu to index the dimension. So it's the number of vertices times the number of dimensions, right? That's how big the configuration space is, right? That's how big. Okay, and this map is taking us from this space to the constraint space. So let's say there are m constraints. So how many bonds or constraints? There will be m. Okay. ultimately, we want to know if it's possible to change the configuration without changing the energy. And of course, this is a problem that engineers care about. Like if you build bridges, like you really need to understand this really well. So actually a lot of the formalism was developed by bridge builders and then tensegrity folks. So this is people like Bob Connolly and stuff like this that I'm going over if you know their stuff. Okay, so ultimately, we want to know, can we change the configuration without increasing the energy? That would be floppy, right? That's the question that we want to explain. Okay? This is floppy. Then floppy. And that's the formal definition of floppy. Okay. So this means that we have to consider a variation in energy, right? Variation du, right? And we care about that variation for any change in the xi. Okay. But since u is a function of f alpha, right? That's how we wrote it, right? It suffices, although I'm going to say usually, we have a paper on when this usually works. It usually suffices, although not always, and that's interesting, to check whether there are any variations of the F alpha that cost zero energy. And at the end, if you want to talk to me about why I have to write usually, I can tell you about it. Okay, so this in the language of engineers is called structural rigidity. So this checking whether dF alpha, whether change to bonds that cost zero, that the changes to bonds that are basically zero. Actually, I wrote that wrong. It's not cost zero energy. I'm not talking about energy anymore. dF alpha that are zero, sorry. And this is called structural rigidity. So if you want to go and do some reading on it, that's what it's called. Okay, so then our goal is, let's just write out this variation in dF alpha. Well, it's the sum over I and mu of the partial derivatives of these constraints with respect to the degrees of freedom times that set of displacements, right? Plus higher order terms. Great. Okay, and the question we're asking, just to rewrite it in math, is does there exist a dxi mu such that df alpha equals zero? Right, that variation was bad. Okay. Okay. And this object is the key object. Note that this object, R alpha I mu, which is defined as dF alpha dxi mu, and which is called the rigidity matrix, is the key thing to think about. And it is exactly this map. So I'll come back to what I just wrote, but I'm going to show you the map again. It's the first order map, right? It tells you how to go from changes in the configurational degrees of freedom to changes in the constraints. Cool? Yeah. I will talk, that's a really good question. I will talk about that in just a moment, how to deal with that particular question. Okay? We'll do it in terms of examples. Great. Okay. So this is the rigidity matrix. It is our map from configuration space to constraint space. And it tells you how changes to the xi's alter the bond. So let's just just for pedagogical completeness, write out a picture for ourselves what this thing looks like. So this is some variation in the configuration. So maybe 1 in the x direction, I vary the vertex 1 in the y direction, I vary vertex 2 in the x direction. I'm writing it out for a 2D system here. And this is dxn x, dx, and y, right? And then this matrix is this matrix, df1 by dx1x, df1 by dx1y, you know, etc. And then this is dfm, they're m constraints by dx1x, okay? And this is dfm by dxny. So, right, this is our R, and we're dot producting it with this dx vector, right? So this is a matrix. And of course, it's rectangular, right? It has m rows, and it has n times d columns. Yeah. Yes, you're right. It's a differential of, it's the linear, you're exactly right. I'm using language a little loosely. It's precisely the linearized differential. Yes, but I'm using the word mapping just to mean it takes me from this space to that space a little more generally, but thank you. Yes. Okay, so R is rectangular. Okay, yay. Okay, and now we can answer our question. Okay, our question is are there any set of displacements that don't change any of the constraints? I'll be right there. So the question is there a set of displacements dx for which this is 0? Of course, this means that there exists a delta x in the right null space of R. And if there does exist such a thing, these dx are called linear zero modes. And I will refer to them as LZM sometimes for the rest of this lecture and tomorrow. One more thing, and then I'll answer questions. Let N0 be the number of independent linear zero modes. Okay, I'll put a little blue box around this thing because it'll show up later. Okay, yes. Oh, yeah. So I apologize. This is the notation in the field. You can think that I've basically turned this pair of indices. I've listed that this is the way everyone does it. I'm sorry. This I mu is indexing n times d. So there's n i's and d mu's. So this is just like one variable really, but people like to distinguish because it has a special structure. It turns out that's useful later sometime that I'm just use as a list. So I put x mu equals y, etc. It's a good point. Yes. Such a good question. I think we'll get to there today maybe. It's not, but it almost is. Okay. The question was, is R transpose R the dynamical matrix that we care about? And it's not quite, but you're very close. It's almost it. Okay. Yeah. Okay. Great. Okay. So, because obviously I'm doing this in a very linear algebra-y way, we could also consider what's in the left null space. Could also consider the map that takes us, and I'm using map again loosely. It's R transpose. It's actually the linear differential, but fine. That takes us from constraint space to configuration, and that's R transpose. Okay, and we can ask, does there exist a set of perturbations to the bonds that do not cause changes to the constraints? Okay, and so the units of the bond, these bonds are basically forces or tensions. So this is a set of sort of tensions on the bonds, right, that don't perturb the constraints. Okay, so that would mean that 0 is equal to R transpose dot, and I'm going to use sigma for these objects that live in bond space. Okay, which is equal to R transpose times sigma, right? And there's M of these sigmas. So this is sigma 1, sigma M, right? And this is, again, R transpose. So I know you know how to do this, but just to make sure we're all on the same page, this is dF1 now by dxny, right? So this is dot, 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 dot. So this is now the transpose. So this is nd and this is m for this rectangular matrix, right? Does that equal 0? Okay. And so I've called this perturbation to the bond sigma, and I'll use that notation for the rest of the lecture. Okay. Yeah, I'm basically asking, is there a set of basically forces or tensions that I can put on each bond so that it doesn't result in any changes to any of the vertices? That's the question I'm asking. Okay. Yeah. So what I'm asking, so what I'm saying is that envision that you lived so in physics, we often prioritize the configuration as the things I can change. But in biology, there's no reason that you can't change the tensions along an interface between two cells. Actually, that's very easy. And so I'm just saying, if I were able to go in and view that, like in some other world, as something I could go in and change, you can ask, is there a set of tensions? And in bridges and stuff, you can actually think about putting pre-stress in elements of tensegrity structures or bridges. So it's a very natural thing to ask. If I go in and put tensions on a structure, is there a set of tensions I can put in there so none of the degrees of freedom change, the configurational degrees of freedom change? So like my bridge stays in exactly the same place, even if I put those tensions on the system. Oh, I used the wrong word. That's what you're telling me. No, I think you're right. So what you're saying is that does not change changes to the configuration. That's what you're telling me. You're exactly right. I wrote the wrong word. Sorry. I went through all of that and you were just telling me I put the word wrong. Yeah, sorry. My bad. Okay. So if these sigma exist, these sigma are called states of self-stress. Okay. This will come up a whole bunch later. Okay. So there are sets of tensions on the bonds that don't move any of the vertices. Okay. They are in the right null space of RT, and that means they're in the left null space of R. So equivalently, these sigma are also, I could write them this way. Okay. All good. Okay. Let NSS be the number of independent states of self-stress. Okay, great. Now, all of that was for the following thing. Now, finally, we're prepared to use the rank nullity theorem. Now we can use the rank nullity theorem to derive constraint counting and to add an extension that is useful. To derive, okay? So rank nullity theorem, oh, yes. Yeah, it's linear here. So all I'm saying is that if I just, this particular first order so it's not true in general, but I'm basically asking to linear order, how do the forces impact the constraints and how the constraints impact the forces? This works. It's just the. Yes, that is a good question. So again, maybe on Wednesday, there is a generalization of what I just showed you to things that aren't quadratic, because there's an underlying geometry and geometric manifold that describes features of this rigidity transition. So there is an extension where it doesn't have to be harmonic. I'm just going through it in the harmonic case because it's a lot easier. Good question though. Okay, great. Okay, so what's the rank nullity theorem, right? It says that the rank of R plus the null of R has to be equal to the dim of R, right? Okay, but this is also equal to the dim of R transpose, which is also equal to the rank of R transpose plus the null of R transpose. Okay, and this says then that M plus N0 has to be equal to N times D plus NSS. Or, in other words, the number of zero modes in my system has to be equal to N times D minus M plus the number of states of self-stress in my system. And this is the formal expression for what's called Maxwell-Calodyne constraint counting. And there's a nice, Tom Lubensky and collaborators have a nice article about this in 2015 that goes through all of this in some detail. Okay. So, are you all okay? Was this way too slow or was it okay? Give me a thumbs up if it was a reasonable pace, a thumbs down if it was too slow. Okay. And if it was terrible, I don't know what to tell me. Like, you got to give me like some facial expression or something. I will look at facial expressions now. Okay. All right. So the reason that we did this is because this breaks. Okay. But before I tell you how it breaks, I'm going to spend the next 15 minutes giving you examples of how it doesn't break. And then at the very end, I'll tell you it breaks, and then you'll be excited for the lecture tomorrow to explain why it breaks. Okay? Yes. Oh, it's just because if you go through and you look for matrices, ranks are easy, right? And so I showed you in each of these pictures of these matrices, like it's this one, R is M rows and N times D columns, right? And so if the rank of an M by N matrix and M by ND matrix is just the number of rows, right? For matrix. Yeah, exactly, right? This is all of the, I'm not going through, of course, these things I'm saying are not true in general, but they are certainly true for this matrix I'm showing you right now. Okay, so this one is easy. Yes? Yes, and I was actually just going to go through the example for jam spheres. So let's go through exactly the question that you just asked, which is, how does this work? So we'll do some examples. So let's do jam spheres first. Because yes, I need to make the point that this is exactly what we derived earlier. So when do particles become rigid? Jammed particles become rigid. Okay, so in this case, I want to know, I've defined rigidity here is N0 equals 0. Because if I have no linear zero modes, then I should be rigid is the idea. Although we'll find out that's not quite true in a moment. But anyway, let's assume that it's true. Then I have M in this case is N times Z over 2, right? That's the number of constraints in the system. It's the number of particles times connectivity over 2. Okay, and then I'm just going to use my formula. N0 is ND minus NZ over 2 plus NSS. Okay, and so I want this to be 0 when it becomes rigid. The key thing is that states of self-stress in general occur when I have tension on bonds. And either you can believe me or you can look at it numerically or whatever, but in general, there is no states of self-stress in jammed particles right at the transition point. So this object is also 0 there. Okay, And if those two things are the case, then I rederive the isostatic condition. So when ND equals NZC over 2, and we rederive that ZC equals 2 times D. Okay, and if Z is less than ZC, I'm underconstrained. This is just the language people use in the literature. Underconstrained. And if Z is greater than ZC, I am overconstrained. And you'll notice that in Professor Das's lectures, she focused on systems that were overconstrained. So they had bending degrees of freedom and other features that put them in the overconstrained class. People often think about diluted triangular networks. So they take a triangular network and they go to the limit that you start to approach this EC. And you can understand a lot of properties in the overconstrained limit using effective medium theory. Okay, so that's the limit that you were in for most of Professor Das's lectures. Okay, so it works. Okay, but the key thing is recall, this all came from considering first order perturbations to the constraints. And it works. Those are the two things to remember. Okay, this is called first order rigidity. And it's a little bit of a pain, okay? Because let me tell you something right now. This is what the language, I'll be with you in just a minute. This is the language that's used by the engineers. They call it first order rigidity. But of course, it's different from a first order phase transition, right? Jammed particle packings actually show a mixed character between first order and second order phase transitions. So from now on, when I talk about order of rigidity, I'm talking about the derivatives that I have to take of the constraints with respect to the degrees of freedom, not some magnetization Ising model something, okay? And there's a question. Yeah. It's continuous there. So that it does make sense. We'll talk about cases where other systems where it's 0, but then it jumps right at the transition. So it doesn't have to be continuous, but in jam particles it is. And that's one way of thinking about why it might be the case. Yes. Oh, compression is also fine. Yeah, no, sorry, I misspoke. I just meant that there was a stress, some forces on the bond. It's easier for many people to think of tensions than compressions, but either one is fine here. Sorry, I should have been more clear. Okay, great. Okay, so let's do another example. Okay, example number 2. Okay, it's a 4-bar linkage. Okay, and I want you to work with your neighbor for the next 5 minutes and write down the number of degrees of freedom. This is in 2D, so this is a 2D frame, a 2-dimensional frame, right? And I want you to write down the number of degrees of freedom and the number of constraints, and then derive the number of zero modes and tell me what they are. Okay, so work with a partner, turn to your neighbor. You should just take a minute, make sure you think. Yeah. You're thinking about moving each of the vertices. They're connected by like springs or constraints or something. Yeah.
Yeah, but they cut it stuff.
Got everybody talking the last 7 minutes of lecture.
All right, I'm going to give you one more minute before we're going to come back together and discuss. One more minute, just to give you time frame. Yeah, 4. Yep, good job. Okay. But now you got to tell me what they are. But where did the 4 come from? Yeah. Yeah. I mean, the challenge in asking it this way is actually any linear combination of the 4 is totally the obvious way to think about what they are. So that's why it's a good open question, is because people can have different answers and they're actually right. But I think there's a way to think about the answer that's instructive for the rest of the talk. That don't change the lengths, exactly. Yeah. So, all right.
Yeah, like where are the force located?
Okay. All right, folks. So how many degrees of freedom are there for this 2-dimensional set of 4 vertices? 8, right? Because it's 2 dimensions times 4 vertices, and that's 8 degrees of freedom. Perfect. Good job. Okay. You were listening. Okay. How many constraints are in this 4-bar network? 4. There are 4 bonds. So you can think about these actually, as I mentioned before, it doesn't matter if they're harmonic springs actually, but you can think about them as harmonic springs. So there's 4 constraints. So how many 0 modes are there? 4. You had to say that there weren't any states of self-stress, and we can come back to that. But it's true. There are 4 0 modes. 8 minus 4 is 4. Can anybody think there's actually a challenge now that I have 4 0 modes is that any linear combination of those 4 0 modes will also be a 0 mode. But does anybody have like a nice way of describing 4 different modes in this system? I saw Carlos first, but that's because I know you. Go ahead, I'll embarrass you. Go ahead. Okay. Go ahead. Perfect. That is a great way, I think, about thinking it, because you also asked the question about what about rigid body motions, right? So this is your answer. All of these systems always, as long as I haven't fixed a point, sometimes the engineers will fix a point and then that changes things. But as long as I haven't fixed a point, you're going to have all of the rigid body motions that you all know and love and have thought about. So those are 3. In 2D, there's up and down, rigid body, left and right rigid body, and 1 rotation rigid body. So there's 3 rigid body motions, right? So I'm going to draw little pictures of those, right? It's up, down, it's left, right, and then there's 1 rotation, okay? And then you said 1 shear mode, right? And so there's a couple of different ways to draw it. If I sort of draw the box like this, I'll try to draw a box. And then I put in a shear mode like this, I can see that I can do this displacement of the vertices and not change any of the lengths of the bonds for a small perturbation. Cool? Everybody agrees that that shear mode is okay. Okay, so these are the 4 0 modes. Yes? It's a really good question, actually. And on the 3rd day, I might talk about the fact that that is true and exactly what you said is true gives you a nice sort of stereographic projection that's important for thinking about this problem later. But so yes, but let me just say that, okay, for all intents and purposes, I basically know what these 0 modes are. I can think about them as in the null space of this object for here. It's okay. Okay. In the 3 minutes we have left, I have 3 minutes, right? Margaret, I have 3 minutes? Great. Okay, let's do another example. This one will be super fast because you already all know what you're doing. Example 3, okay, which is what happens if I add a bond across here to this thing, right? What do I get now? I'm not going to make you do it again, you all know, right? The number of degrees of freedom is still the same. The number of constraints, I've added one, right? Constraints, I've added one. That means I only have 3 zero modes, and those are the rigid body rotations. So this thing is rigid, right? Yay. There's only people in the field call it, there's only sort of trivial motions, which are the rigid body motions. And sometimes, even though it's a little bit complicated, sometimes engineers will make certain other things trivial in order to do some things. But okay, for here, we're calling trivial, the trivial ones are the rigid body motions. Okay, so example 4, and I will leave you with this. Yeah.
How can you tell in 3 there's no?
Well, if I have 3 rigid body motions, then NSS by the Maxwell-Kellendine constraint counting would tell me it has to be 0, actually. Yeah, so there's, I think Professor Das even talked about it, the pebble game a little bit. So there's some things that there's some way of taking more complex networks and trying to figure out sort of piece by piece which parts are rigid and which parts are not. I'm not going to focus on that here, but there are ways, algorithms for doing that for larger networks. Yeah. Exactly. Yeah, you're exactly right. And I've been with that notation, but you're exactly right. What I mean, and actually, of course, for isostatic systems, I've actually, in like, this is the dirty secret in the field, like you always subtract off the rigid body rotations when you do the computation. Like you actually have 3 extra lying around. And so actually, if you care about finite size scaling and stuff, you have to pay attention to those rigid body motions depending on the dimensionality of your system. So I also lied about it for the isostatic. Actually, everyone lies about it for the isostatic point, just so you know. Because you assume n is large, and so those extra 3 don't matter. Yeah.
That would add like another number of constraints, so it would change NO to 2, but you still have your.
Oh, that's great. You actually get a state of self-stress. That's beautiful. That's exactly, if we had time, I was going to do that example, but you can write it down for yourself. You still have those 3 rigid body rotations, but you introduce a state of self-stress. So NS goes up. Okay. So let me say, I know but I'm going to just show you an example and then not talk about it. I have 0 minutes left, but I want you to think about this overnight, and I want it to bother you because it bothered me. Okay. So here's the example. It's exactly the same 4-bar linkage, but now I've stretched it out so that the distance, so if this was, say, points 1, 2, 3, and 4, I've changed the geometry, not the topology, nothing that we have counted. I've just changed the geometry of my system so that now the length of between 1 and 4 is approximately 3 times the rest length that these individual springs prefer. Right? And you all know that if I take that one and I move it past 3 times the rest length of the springs, this thing is going to be rigid. You know it. If I take 1 and 4, right, and I displace them so that their length between the 2 of them is greater than, say, the rest lengths of the springs of 1 to 2, 2 to 3, 3 to 4, it's going to be rigid. But your constraint counting says nothing. It's exactly the same as it was for the 4-bar linkage above. What the heck? Okay, that's it. That's it for today. So tomorrow we'll answer what the heck. Okay? Yeah. Yes. Yes, then you could think of the number, it being the number of redundant bonds in the system. But you have to sort of be careful because then that's why I mentioned the pebble game to Leo, is because actually figuring out which bonds are redundant is a local operation. Yeah, so it's actually rigidity percolation is a complex thing for this exact reason, which is why I didn't really talk about it too much. You're exactly right, yeah. Okay, thanks everyone. See you tomorrow.